In this module, we are going to discuss the concept of sparseness as applied to general contingency tables. We have seen the concept of sparseness once more in this paper on GLMs in the context of the deviance function. We have seen that when we have binomial data and ungrouped proportions, in this case, there is a problem related to using the deviance due to the fact that all the ni are equal to 1. In this module, we will look at the concept of sparseness as it applies to a general contingency table. We will first look at the consequences for ML estimators, and although the consequences are not necessarily fatal, the problem with sparseness is that it can lead to problems with software, and software can often report convergence when in fact there hasn't been a convergence. We shall also look at the consequences of sparseness on goodness of fit statistics and see that it can depend upon the specific nature of the sparseness and the purpose of the goodness of fit. Finally, we shall look at the consequences of a very popular technique which involves an ad hoc addition of a constant to the cell frequencies. Learning objectives for this module. We shall first look at the two different types of zeros which can occur in cell counts, firstly structural and secondly sampling zeros. We shall make a distinction between the two, and for the remainder of the discussion shall confine ourselves to the occurrence of sampling zeros and their consequences. Next, we will look at the consequences of sampling zeros on ML estimation. After this, we shall look at the consequences on various measures of goodness of fit. Finally, we shall look at the technique, which is ad hoc but popular, of getting around the problem by adding a constant to the various zero cell counts. A sparse contingency table occurs when some of the cell counts are small. Small cell counts can occur in two situations. Firstly, if the sample size itself is small, and secondly, if the sample size is large, but the number of categories is also large. Sparseness in contingency tables has an implication for model fitting, and this is what we shall explore in the remainder of this module. Let us first make a distinction between the different types of empty cells which may occur. A cell may be empty due to two different kinds of zeros. We make a distinction between sampling zeros and structural zeros. Sampling zeros are the more common types of zeros, and it means that even though ni is equal to 0, the corresponding expected frequency mu I is positive. An empty cell occurs as an artifact of sampling. A different kind of zero occurs if the corresponding mu I is equal to 0, and this is called a structural zero. This can occur in some situations where, by the nature of the data, certain cells are bound to have structurally zero counts. Say, for example, we are looking at a cross classification of cancer patients by their gender, race, and type of cancer. As some cancers such as prostate cancer, ovarian cancer are gender specific, it is certain that some of the cells will have structural zeros. The problem of structural zeros is rather different, and For the remainder of the discussion, we shall restrict ourselves to sampling zeros. Sampling zeros are a normal part of the data set. A count of 0, for example, is quite permissible under a Poisson or a multinomial variate. Sampling zeros are more common than structural zeros. Sampling zeros can affect the existence of ML estimates of log linear and logit model parameters. Haberman, in his research, showed the following results for Poisson sampling, and these results will also apply to the case of multinomial sampling. Firstly, the log likelihood function is a strictly concave function of log mu, mu denoting the vector of expected cell counts. If a ML estimate of mu exists, it is unique and satisfies the likelihood equations x prime n equal to x prime mu hat, where n denotes the corresponding vector of observed cell counts, mu hat the estimated expected values, and x the design matrix. Conversely, if mu hat satisfies the model and also the likelihood equations, it is the ML estimate of mu. If all ni is greater than 0, ML estimates of log linear model parameters exist. Suppose that ML parameter estimates exist for a log linear model that equates observed and fitted counts in certain marginal tables, then those marginal tables have uniformly positive counts. If ML estimates exist for a model M, then they also exist for any special case of M. Finally, for any log linear model, the ML estimate mu hat are identical for multinomial and independent Poisson sampling, and those estimates exist in the same situation. For details of these results, you are referred to the discussion on empty cells and sparseness in modeling contingency tables in the book by Regression. Haberman also showed that the supremum of the likelihood function is always finite, and this motivated him to define extended maximum likelihood estimators of mu. Extended maximum likelihood estimators of mu always exist but may equal 0. And because they can fall on the boundary, they need not have the same properties as regular ML estimation. This is an example of data for which ML estimates do not exist. The example has been provided by Regression in his book and in the chapter on modeling contingency tables. For unsaturated models by results 3 and 4, ML estimates exist when all ni are positive and do not exist when any count is 0 in the set of sufficient marginal tables. If at least one ni is 0 but the sufficient marginal counts are all positive, in this situation, for a hierarchical log linear model, Glonek showed the positivity of the sufficient counts means the existence of the ML estimates if and only if the model is decomposable. Models having all pairs of variables associated are more complex. For example, for model xy, xz, yz, for example, ML estimates exist when only one ni is equal to 0, but may not exist when at least 2 cells are empty. An infinite value of the ML parameter estimate means that the ML fitted values equal 0 in some of the cells and some of the OR estimates are equal to infinity or 0. One indicator of this is non-convergence of the corresponding iterative fitting procedure, typically because an estimate keeps increasing without bound from iteration to iteration. Unfortunately, software is often fooled by this kind of behavior due to the likelihood being nearly flat and the log likelihood having very slight curvature. The consequence of this is that the estimated standard errors based on inverting the information matrix are extremely large as well as numerically unstable. Thus, a problem with having sparse data is that one might not realize that the true estimated effect is infinite and report estimated effects in statistical inference that are highly unstable. Here we see the results of a clinical trial conducted at 5 centers. We wish to compare an active drug to placebo for treating fungal infections. The response is assumed to be binary, that is, success or failure. So Y here denotes response, X denotes treatment, and Z denotes center. Centers 1 and 3 had 0 successes. So the 5x2 marginal table, which relates response to center, contains 0 counts. The last 2 columns of the table show this marginal table. Infinite MLE will occur for terms in the log linear or logit model containing YZ associations. An example is the logit model, logit of probability y equal to 1, given x equal to I and z equal to k. The counts in the 2x2 marginal table relating response to treatment shown in the bottom panel of the table are all positive. The empty cells affect the center estimates but not the treatment estimates with this logit model. Now, empty cells in sparse tables need not necessarily affect parameter estimates as we have seen on the previous slide, but they can cause havoc to the sampling distributions of goodness of fit statistics. In particular, they affect the assumption of the chi-squared distribution. The adequacy of the chi-squared distribution depends both on small n as well as on capital N, where capital N denotes the fixed number of cells. Cochrane in 1954 studied the chi-squared approximation in several articles. He suggested that to test independence with greater than 1 degrees of freedom, a minimum expected value of mu I equal to 1 is permissible as long as no more than about 20% of the mu I are less than 5. Further research on the behavior of goodness of fit statistics have been conducted by Kokla and Lance. They showed that the chi-square approximation applies with smaller n and more sparse tables than the g-square goodness of fit statistic. The distribution of the goodness of fit statistic is usually poorly approximated when small n by capital N is less than 5. When most of the mu I are smaller than 0.5, the g-squared statistic tends to give a highly conservative test. In general, the size of the ratio small n by capital N that leads to adequate chi-square approximations will tend to decrease as capital N increases. However, the approximation tends to be poor for sparse tables containing both small as well as moderately large mu I. For further research and further cases of this, consider the papers by Haberman, 1988, Cressy and Reed, 1989, and Lowell in 1984. For fixed N and capital N, the chi-squared approximation is better for tests with smaller degrees of freedom. Model-based statistics, for example, model-based statistics which compare two models M0 and M1, generally depend on the data only through the fitted values, and hence only through the minimal sufficient statistics. For most log linear model, these statistics are the marginal tables, and the marginal totals will tend to be nearly normally distributed even if the single cell counts are not so. Thus, the chi-squared statistics or the goodness of fit statistics for comparing two models will tend to converge to the limited chi-square distribution more quickly than the chi-squares or goodness of fit statistics for testing goodness of fit of a single model, as these will also depend on the individual cell count. Theoretical justification for this is provided by Haberman in his 1977 paper. As an alternative method in situations where there are sparse data, we can consider one of two classes of methods. The first is to use exact small sample methods, and the second is to use Monte Carlo based methods. For details of this, see the research by Booth and Butler in 1999, Foster et al. 1996, Kim and Agresti 1997, and Mehta et al. 1988. A third alternative exists, which is to use sparse asymptotic approximations, not the standard kind of asymptotics, but asymptotics that apply when the number of cells capital N increases as the total number of observations small n increases. For details of such asymptotics, you are referred to the papers by Kohler and Lance 1980, Kohler 1986, and McCulloch 1986. Finally, let us look at a very popular, though ad hoc technique, which is often used in situations where there are sparse cell counts. Now note that one way of working around this problem and getting finite estimates of all the effects as well as ensuring convergence of the fitting algorithms is to add a small ad hoc constant to the cell counts. More often than not, this constant is half. This can be shown to lead to bias reduction for estimating odds ratios in 2x2 table, and the details have been worked out by Gart in 1966 and Gart and Zwiefel in 1967. However, adding half to a cell before fitting an unsaturated model can smooth the data and thus have consequences for assumptions about the sampling distribution. The consequence is that there is a conservative influence on the estimated effects and test statistic, and the effect can be severe in case there are a large number of cells. The general recommendation is that when ordinary ML estimates of an odds ratio turn out to be infinite, the estimate after adding half to each cell is finite. However, this is not recommended, and it is more sensible to use an upper bound of infinity for the odds ratio, as we have no sample evidence to suggest that the odds ratio falls below any given value. When in doubt, it is recommended to perform a sensitivity analysis. For example, each possibly influential observation can be deleted or moved using perturbation diagnostics. Such perturbation influence diagnostics for GLMs have been worked out by Williams in his 1987 paper. In this module, we have looked at sparseness and its consequences for a general contingency table. We have first defined two alternative types of sparseness. One, which is called sampling sparseness, arises when some of the cell frequencies are zero, although the underlying rates of proportions are not necessarily zero. A different type of sparseness arises in case we have structural zeros. This is a situation which is more complex, and it arises because some of the mu i's are zero. This is beyond the scope of this module. So for the remainder of the module, we have considered the case of sampling zeros and their consequences for estimation, goodness of fit. Finally, we have looked at the consequences of sparseness and the ad hoc solution of adding a positive constant to the cell frequencies. It appears that the consequences depend on the exact nature of sparseness and the purpose for which the corresponding statistic is being used.